In this video, I'm going to do the A part of this question. The question is asking, consider the basic bipolar current mirror of figure 8.7. The picture is right here. For the case in which Q1 and Q2 are identical devices having IS is equal to 10 to the power minus 17 ampere. A part is asking, assuming the transistor beta is very high, find the range of VBE and IO corresponding to IREF increasing from 10 microampere to 10 milliampere. Assume that a Q2 remains in the active mode and neglect the early effect. Okay, so here they are asking us to find out the VBE and I0 range when the IREF current is increasing from 10 microampere to 10 milliampere. Okay, and this is the information provided. We have the IS current provided, that is 10 to the power minus 17 ampere, and there's a relation between IS current and I reference that is given by I reference is equal to IS times e power VBE over VT. This information is good for us because from this one we can find the VBE value, because we have the I reference available, that is 10 microampere to 10 milliampere, and VBE is what we are trying to find. We have the question asking us to find out VBE and I output, but this equation is useful to find out VBE. Okay, and VT is a constant value, that's a thermal voltage, that's always 25 millivoltage. So we have all the values are known except this VBE value, so we can rearrange this equation and solve for this VBE. So in order to solve for this VBE, now we have to get rid of this e power and bring it down. In order to do that, I can take ln both sides. So if I take ln both sides, this is ln I reference is equal to ln IS times e power VB over VT. Now when we have ln multiply, that is equal to, if we separate, that's equal to addition. So we can also say ln I reference is equal to ln IS plus ln e power VB over VT. Okay, here ln and e cancels each other. That is like, okay, we cannot say just cancel. What we can do is we can bring this to the front. So if we say ln IREF, but whenever you see ln and e, that's like canceling each other, that look like that, and this is like ln IS and then plus VB over VT ln e. Ln e is 1, and since we are interested in VB, we can move this one to the other side. So this is ln I reference minus ln IS, that's equal to VB over VT, because this one is equal to just 1. And when we have subtraction in ln, that is equivalent to division. So ln I reference over IS. Okay, so this is the equation, and if we write in terms of VBE, then VBE is equal to VT times ln I reference over IS. Now we have the equation, we have to just plug in the values we have and solve for the VBE. Now here we are interested in what is the VBE value when 10 microampere, and also what is the VBE value when I reference is 10 milliampere, because that is the range we are looking for. We want to know the range. So I go to the new page, and then VBE is equal to VT ln I reference over IS. VT is 25 millivoltage, so 25 times 10 to the power minus 3 right here. Okay, and then ln I reference, first we are looking at for 10 microampere. 10 microampere is 10 times 10 to the power minus 6 ampere, and IS is given to us, that is 10 to the power minus 17 ampere. Plug in all this and calculate this value, you will end up getting 0.691 voltage. Okay, so this is when when the I reference is 10 microampere, and also we have another situation, that is when I reference is 10 milliampere. In order to find the drawdown, we can use the same equation, Vt ln I reference over Is, and here Vt is 25 milliampere millivoltage, that is 25 times 10 to the power minus 3, and then ln I reference is 10 milliampere, so 10 times 10 to the power minus 3 divided by Is, that is 10 to the power minus 17, and if you calculate this one, you will end up getting 0.863 voltage. Okay, so the VBE ranges we can mention in the next page, or we can hit say it here. Therefore the VBE ranges, VBE corresponding, okay, you know what, I go to next page and write it clearly because I don't have enough space here. We can say thus the range of VBE corresponding to I reference increasing from 10 microampere to 10 milliampere is 0.691 voltage. Okay, oh, I can write it down here. 0.691 voltage. So the VB should be greater than or equal to 0.691 voltage, and less than or equal to 0.863 voltage, because those are the value we calculated. Okay, so that is for the VBE, and also in the question, if you look at this, the question is asking for the I output as well, IO. So we have to find that one. Now in order to find IO, we have to use another equation that is given by IO is equal to I reference divided by 1 plus 2 over beta. Okay, and if you look at this question right here, it says assuming the transistor beta is very high. So it means whenever they mention that, that means this beta is infinity. So this is also equivalent to I reference 1 plus 2 over infinity. When you divide a number by a very large number, that tend to go to 0. For example, if you divide 1 by 1 million, that's almost like 0.00001 something. So it's like 0. So this is I reference, end up being I reference over 1 plus 0. So we can say I naught is equal to I reference. So which means when I reference is 10 microampere, I naught also 10 microampere. When I reference is 10 milliampere, I naught also 10 milliampere. So it means it's a straightforward. Whatever the I reference we have, that's going to be the I output as well. So we can say therefore the range I naught corresponding to I reference increasing from 10 microampere to 10 milliampere is 10 microampere greater than or equal to I naught less than or equal to 10 milliampere. This is the I naught range. Whatever the I reference range is the I naught range. Okay, and that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.